computer. Maybe faster. Okay, so we're now recording. Let me share the screen, and I'm going to go with my, this should work, iPad. Yeah, good. Okay. Here we go. Now, I'm mostly looking at set 2. We'll go over set 2, and then at the end, if you still have questions from set 1, you can stick around or you can take off, and then all those with set 1 questions. Okay. Now let me open up the chat so I can see if you're saying something to me. But I'd probably easier because I don't see that chat very much. So probably easier if you all just turn, when you have a question, turn your microphone on. It's a lot easier than trying to chat and talk at the same time. Hold on, put this down at the bottom. It's all new. This is a new situation here. And I don't know what, I heard a little buzz there, but I don't know where that's from. I think that's from, I'm gonna unplug that. I think it's from the link maybe to the iPad. Okay, here we go. So I'm sharing the screen. Let's just go through this. I don't have a key. Okay, I'm gonna hit record. I don't have a key yet. I mean, I did, if I could find the old problem and a key to the old problem, I put that on the Facebook group. So we don't have an hour is probably not enough time to go through painstakingly every step, but I know this is on the Facebook group. But we'll quickly talk about it for a second. It looks like it's an equilibrant problem, right? So you're going to have to find how many forces we got here. Hold on, it's been a couple of years since I worked this one. I apologize for hearing that buzz. I hear it too. I don't know how to stop it. So the first thing the crew has to do is stop him from accelerating and get him static relative to the ISS. So Elon hangs out the window, throws a cable around Tiny's waist and pulls with a force. Okay, so we got one force here, blue, and Neil deGrasse holding on to the ISS grabs a pull. Okay, so this is the profile view. So we're looking at not from the top down, but from the side. Brian Cox throws a cable. Okay, so there's our third vector, and then you got to figure out a fourth vector. Okay, so it's just do the stack and rack on those three vectors, find the resultant, and then do the same magnitude and caddy corner quadrant on that to find the equilibrant, because that's what the equilibrant is to the resultant. The equilibrant turns a dynamic moving situation into a static situation. All right. I don't know how much I want to do with this. Let's sketch them at least. And all you need here is a sketch, and then you draw your three right triangles. So the first one's, I always draw the big dog first, which is, it looks like Elon, 420 newtons, 40 degrees above right horizontal. So he looks something like this. We'll make that the longest arrow. Okay, Neil deGrasse, he's at 25 degrees below left horizontal at 280. So he's something like that. And then we have Brian Cox, 200 at 70 degrees below right. So he's like 70 degrees. He's like that. So you just give me a yes or no on your comments if you're hearing that buzz about once a minute. Is it just me? Hopefully, that'd be great. Ah, crap. Patrick hears it too. All right. So you guys are hearing it. I don't know what to do about that. I guess we'll just have to live with it. All right. So anyway, you have those, and then you follow all the procedures. Yellow there, two negatives and a positive right there. And then just take all the I roofs, J roofs, right? Add up all the I roofs to the I roofs, J roof to the J roofs. Watch your sign, positive, minus. Anyway, there's a key on it. Questions on number 9. shout them out, or I'd prefer you just shout it out. Carson says, let's go on. Maybe thumbs up to go on. Thumbs up to go on. Well, okay. Cole's giving me a thumbs up. Okay, that's fine. Hey, Cole, I don't know. I think you better turn your video off, because it is going to go public. I don't like people seeing you guys on YouTube. All right, because it'll be public. It's a pain in the butt to make it private, because then you never see it, or I got to invite you. So, all right, number 10. 10 is brand new. I'm guessing you tried it, because look, I went around the room enough to know. Okay, I need a ruler. All right, so this one requires a ruler, not a protractor really, but at least a ruler, a decent ruler. And I helped you out there. I moved that MG, and MG. Okay, a cat's out of the bag, and we'll talk about MG. We've mentioned Newton's second law. We're about to get into it, and we'll be into it the rest of the year. But F equals MA. But on this one, so the mg is like what I called in class F sub g, force due to gravity. But since F equals ma, we know that the acceleration on an object being pulled to the earth is g. And so instead of saying F equals ma, we say the weight or the force of gravity is equal to mg. So that's why I just went ahead and called it mg here. All right, in case that throws you. All right, so I repeated mg over here. Now, I've got to redraw the other ones. And so I left that up to you. Daggone it, I need a ruler. Hold on. See, all my stuff, it's gone. I was in boxes at school, and I'm at boxes at home. We'll get that figured out. I'll just do it the other way. Hold on. Okay, I don't really like this, but all right. So now I'm going to redraw in. Okay. 1, 2, 3, 4, 5. Okay. Redraw in over here. And I'll make him blue and smaller than that. All right. 1, 2, 3, 4, 5. What? Okay, that's it. So that's in, redrawn, same orientation. And now I redraw P. So I'm just doing head to tail here. And when I was going around the room, look like a lot of you were doing this. So I'm going to redraw my force of pull, I guess is what it is. Okay, almost 2. All right, and that's the right orientation. So I'll make this guy black. So 1 and almost 2. Got her. So that is my F sub P. Okay, so all I got left is this friction force. Now I stick the friction force on there. Here's why I was worried about this problem, whether it's going to work or not, because of accuracy. All right, 1. Bring this over. I mean, with this iPad, I can be pretty. Oh, mama. Let's change my colors up. I thought I was in trouble there for a minute. I was making excuses. All right, look. Kaboom. That friction hooks up perfectly with the mg. And so, as you know, that means no resultant. Which means that this object is, if it's either not moving at all or it's sliding at a constant rate. And so either way, though, it's asking you to help it accelerate. It won't accelerate. Okay, well, I end up working that whole problem. All right, questions on that problem? Ask, or we're going to have to do a thumbs up in a second. Uh-oh. Okay, so let's do a thumbs up then if we're gonna ready to move on. Okay. Yeah, okay. Yeah, you can always go back and watch it again. Heck, I worked that daggone thing. Oh, come on, man. I don't want to do this. That's what you just said, right? I don't want to do this. But I honestly, I've about halfway written the test. So this is on the chopping block. It could stay in, but there's so much to cover. But I like to put a derivation in. So I could have you do, okay, it's either this or deriving the second green. But if that wasn't on the first set, then I guess it's going to be this. One of those two derivations. Okay. So here, okay, especially second hour, because first time I go through that, I didn't really go through it much last year. You realize last year students, I was just thinking about this today, they didn't get any history, not one bit. I didn't have time. I had to punt. So they were never tested over history. They never had to hear me going on and on about Einstein or Hubble or anybody. And I realized last year I really missed it. So I brought it back this year, and it slows us down. But we're still way ahead of them because it was such a horrible year, All right, so you were there. Now, I'll show you what I do want in this. I do want you to give me the secant line, and I didn't do this in second hour. I want you to give me the secant line. Okay. This was all Mr. Patrick's fault. Oh, he wasn't there at the time? Okay. Okay, he'll be my scapegoat later. Okay, so you got to draw that secant line, and the slope of secant, as you know, is delta is a V bar, delta X over delta T. But you've got to show that show how you go from V bar to instantaneous. And really, these notes, this is in your notebook. So if you were there that day, if not, it's on the notes. You can look it up on the screen, on the, that cover thing I always put at the front of class. That's there for you to see when you go to Facebook. So you'll go, oh, here's the things we were talking about. And then you could go, it's going to get more detail down below. So you can use it as to help you scan, like you go, oh, I needed that thing on derivation. Then you can go back and find the screenshot. And if there's captions, I think that stuff is searchable. So you can just, in the Windows search, in the Facebook group, search derivations or search derivative or something, and then all those will pop up. Anyway, you got to go through the steps. I don't have them with me, but the screenshot is on a previous. So let's just go on, because there's nothing really, it's not a problem. Are you guys good? I mean, unless you want me to go on and on about it. Okay, well, okay. Two people say we're good, but Caleb's always ready to move on. Okay, all right, let's keep going. No, I'm just messing with you, Caleb. But you are a tennis player, though, right? So, all right. So these, as we know, are lickety split, kaboom, kaboom, right? You all know this, but let's just verify because it's fun. Chain rule. I mean, not chain rule. We'll learn the chain rule tomorrow. It's not so fun. The power rule is pretty mindless once you get used to it. So what's the velocity? So that's x dot, which equals v. Bring the 3 down, 1/2. Oh, okay. This is just the pink equation for velocity. 1/2. Oh, little almost. Yeah, it's pink. I should do it in pink, but that's all right. That's confusing. I'm doing it in orange, and it's a pink equation. I got to commit to the coloring scheme. Oh, pink. Pink. All right. I'm problem is I'm colorblind. I think that's pink. All right, so 1/2, close enough. 1/2 J naught T squared plus A naught T plus V naught. So, you know, it's basically the second pink is the top equation on orange. You know, it's the pattern. Okay. So that was it. All right, well, let's keep going. 13. Okay, so now we have kind of a real problem. We got to find velocity. This is a situation. It's a snap situation. And I've been looking at snap tonight, and we've been back and forth on it on the physics show. But I think snap and crackle show why space-time is sticky. That was my conclusion, was space-time itself is sticky. It doesn't, and I put a little blurb on Facebook on our group about that. We'll talk about it tomorrow. Okay, so we bring the 4 down, so we have 1/2. You guys can check me on this. T cubed plus, we check each other, right? 9T squared minus 1/2, and that's feet per second. You got to put the units on the outside, or I would count off. This is only worth 2 points, but if it was worth 10, I would count off 1 each time you didn't do feet per second. Your units on the outside, at least 1. We do it again, so we have 3/2 T squared plus 18T, and then that other one lops off the end, and so that's feet per second squared. And you see, we could go 2 more derivatives. That's why it's a snap situation. Okay. Okay, now 14. Oh, good. Boom, boom. 14, 15, 16. These are quick. They should be pretty quick. You know, I was teaching you, and I taught you the purple, the 1/24th. And so if that's fresh in your mind, cool. But a lot of people, it's not. Just to remember, oh, that's the coefficient, and that's all for orange. It's going to be 1/2 A, and for, so you can just always, the simplest way to do these, that you don't have to sit there trying to remember some formula, is just to go ahead and do the derivatives. So this looks like an orange situation, but I'll go ahead and do it. So tell you the truth, if it's an orange situation, I'm not going to do it because it's too easy. So this is my orange. Let's not go purple. Orange. Okay. So this is my so that's 3 meters. It's just, that's initial condition. That's my initial velocity, -6. I get all of that. And you should put units on here. So that's meters per second. And then A, remember that's 1/2 A. So therefore A is 4 meters per second squared. Good. Who's good? Everybody good on 14? Thumbs are going up everywhere. All right, now let's go over here, and I'll do it in the color that it should be, just because that's kind of my way. 15. What are the initial conditions of this third order pink equation? Now, okay. I could go, let's see, that's 1/6 for the first one, and then okay, I will, because it's still just looking at it, it's still the easiest way to do it. So X naught is -8 feet. That's the next one up, is see if it's, yeah, so it'd be V. So V naught is 9 feet per second. The next one up is gone, because that's like saying 0T squared. So the acceleration is gone. We go right to jerk, and then we know that 2 times jerk, or sorry, 1/6 times jerk, or jerk over a 1/6, is equal to 2. So then jerk is 12. So jerk is 12 feet per second cubed. So I think I'm okay to doing it up to pink, but it's kind of, I doubt anybody's going to remember the snap and and then throw in a 120th for crackle.
I have a question about that.
Yeah.
So is what are the fractions for it? Is it like kind of like a proportion?
Yeah.
Like
So like 1/6, in a, yeah, if I'm solving for X in a pink, it's 1/6 jerk, whatever jerk naught is, whatever initial jerk is, if there is initial jerk, T cubed, plus, and then you'd say 1/2 A naught T squared plus V naught T plus X naught. So it just, and that's on the hanging from the ceiling. Then there's a purple one above that, and that's snap, and we just call it mythical because I don't want to hang it. It's too daggone long. And by that time, you know the power rule, so you don't need to do that. Once you're on the power rule, you don't need to know all that stuff.
But in the equation, we know that what the velocity is, and we know what the X naught is. So is like, I'm saying, like, is it proportional? So we know that 1 is 9 and 1 is 8, kind of like if you had like 3 to 4 and then it was 12 to blank. It's kind of like, I'm kind of
It is
confused.
a pattern. It is a pattern. The pattern on those goes, you'd have your naught, right? So say it's X naught. And then that, as far as the pattern, as far as the coefficients go, remember coefficients, the mathematical number, it's 1, then a half, then a 1/6, then 1/24, then 1/120. And no one ever goes past crackle. So I don't know, whatever the next one is, you can follow the pattern. But that has to do with antiderivatives. As you're going, your derivatives as you go down, you do the power rule, and then the opposite of the power rule is the antiderivative. Anywho, let's keep going. It's getting late. We got some, we're doing fine, but we have some tough ones coming. I know a couple of them for sure. 16, what's the initial? Now it gets a little harder. For one thing, that's velocity. So that always throws people. It's like, oh, I started at the top. Ooh. Or they see this and go, oh, I see, that's pink. No. Why isn't it pink? It's cubic. I'm waiting for you to answer. That wasn't rhetorical. Hold on. Okay, keep asking. Keep thinking. Why didn't it? Go ahead.
The question, I missed the question.
The question was, if that's a cubic, I thought when T was cubed, we're dealing with pink equations. So why isn't this a pink equation?
Does it have to do with the units?
Yes. It has to do with that guy, right? I'm not looking at X, I'm looking at V. So when you go up to the X row, it would be T to the 4th. So this makes this a purple, the mythical purple. But my point about the derivative is that you don't need to worry about all that kind of stuff. Just go ahead and say, okay, so V dot, and we can get away with that shortcut because this is all kinematics, is 6T squared minus 10T, and that's it, and it has units, whatever. Well, I guess we do need to put the units. We're going to do it up there. So that's V dot, which is A. And so that's centimeters per minute squared. And then if I do it again, A dot, which is J, not J naught, it's just J, the function of J. And that's 12T minus 10. And the units there are centimeters per minute cubed. And then you can still do it again. So that's when we know we got snap, which I was always putting SM, but then Ayana showed me, no, it's really just S. So this is S naught because this is a constant. So that's 12 centimeters per minute to the 4th. Well, I did all of it. And then I could just put arrows, I guess. They want to know the knots. They want to know the knots. Okay. So J naught then is -10. I read that right off. Let's put a highlighter. I read right there. I get the -10 from that. Oh, no. Yeah, -10 from that. Okay, from that, not from the other one. Sorry. Let's get rid of that. Back out. Okay, so this -10 here. And then, okay, so V naught is written right there. That's easy enough. That's just 3 centimeters per minute. And then we got to get S naught. Well, I did that at the bottom. That's 12 centimeters per minute to the 4th. And yeah. So yeah, because that goes 3, 2. Ooh. Oh, notice they didn't ask for, what if they'd asked for A naught? I should have done that. What's initial acceleration here?
0.
Yeah. Because there is none. There is a constant. So acceleration, so it wasn't accelerating to begin with, but there was jerk and there was snap. It's crazy. Now we get to the 17. Are we good to go? Can we go past 16? Or
yeah. So what you did to solve that was you found the derivative until you got the knot.
So I got down to nothing left.
Okay, and that allowed you to find the knot for all of those.
Yes, because the knot's the thing on the end, the constant.
And on the jerk knot, it would have centimeters per minute cubed.
Oh yeah. The units should have been. I'm being lazy here. Units should have been a stamp because you caught something per minute cubed. Yeah. Good catch. Oh, Patrick's give me a direct, guys. Don't give me direct messages. Because I'm going to read them for everybody unless it's something personal.
So to find the reason you put 3 down.
Yeah. So Patrick gets a stamp too because he asked at the same time you asked. All right, go. Keep going, Cole.
So you put the 3 down because the 3 didn't have like in the V. You knew the V naught.
Yeah, because that's the constant in the velocity.
Yeah, that's the constant. So you had
it's always a V naught on the end, or V naught, or an X naught, or whatever it is on the end is always a naught.
But you kept going down until you found just.
I kept going down till I exhausted all the derivatives.
Yeah. Okay. Yeah.
All right. Now I think people are ready to move on. 17. What are the initial conditions? How are we doing on time? We're good on time, man. I got time to tell lots of stories. I'm kidding. All right. So what are the initial conditions for this third order acceleration equation? Third order acceleration. Okay, so we're in a if that's third order, then second order is jerk, first order is snap. This is a crackle situation. And my argument on the Askey's physics show tonight was any mass above 1 milligrams can't withstand a crackle. And then we're bringing up the idea of bullets in barrels. And we had this problem, right? We said, we looked at that graph. We said, that's at least a snap, probably a crackle. So I guess they can. Anyway. But the whole point was that as you go further up, as you go further into the derivatives, like space, I'm talking about space-time. Space-time's got no problem with position, the displacement. You can be wherever you want. It really doesn't have any problem with velocity either, because it's V naught T. I mean, you get all of velocity. And so that is fine for space-time. But it starts to resist when you try and accelerate something, because that's 1/2 a T squared. And if you try to jerk to push it to make it thrust like a rocket, that's jerk, and that's 1/6 jerk naught. How much jerk you put into the system. You only get 1/6 of it. So it's not as much bang for your buck. You're getting all the velocity you put into it. That's getting used, but only 1/6 of the jerk. And then you go even further, you go to snap, it's 1/24. So it, like, space-time gets this, my point was space-time gets sticky at when you try and accelerate the acceleration, because the force has to be cubic, and that's too hard to. And then a guy from Houston that runs a computer company tells me that his rotators do that. They do snap. I mean, they do go through all the, as they're speeding up as you're running those. So he's explaining that to me. So the point is, this brought up a huge discussion. Still going on, by the way, and I get back, get back into it. All right, so the point is, we're in a crackle situation. So I don't even know. I know it's 120th, but so what? I mean, let's just do the simple thing, do the derivatives. So therefore, jerk is going to be J of t as a function of time is going to be 12t squared minus 7. Okay, that's always soothing to my mind. I don't know, power rule. I guess it reminds me of high school or something. It's very soothing. Miles per second cubed, excuse me, second cubed. And now let's go to, well, snap would be next. And let's see what we get for snap. Oh, just S. I got to get back in the habit of that. So we get 24t. Okay, plus 0. So there's no snap knot. That's why it's not listed up there. And that's miles per second to the 4th. And then we got crackle. And I guess I'm going to go with CR. And that's just 24. So we do know crackle knot. Oh, that's not a function of time. Time got derived away. It's just CR naught is 24 miles per second to the fifth. Okay, so then I can just go, woo, be lazy. That's that. That's that. Oh, and then A naught is right here. There. Mr. Lazy. Try and be nicer to me than that on the test. I'd reward you, you know. You make it really hard to grade your problems. After a while, it starts to irritate me. You might lose a few extra than somebody else because organization's important. I mean, I know. I mean, Cole's handwriting's not quite as bad as mine, but it's pretty bad. But he always blows away tests because he obviously knows what he's doing. But he could be a little more organized, and he knows that, and I know I could be too. But I think I ought to give you more incentive to be organized. Some of you are really organized, and you're dead wrong, and you get decent points. Not as much as somebody be right, but you get pretty good, maybe 10 out of 25 or something. You really were way off, but you were organized, and now you're way off, and that's organization, an important skill. So keep that in mind. Now we're into the crux of the whole matter. Hey, let's knock off. No, I was going to knock off a couple of the easy ones, then come back. Yeah. Let's do that. Let's knock off 19, 20, and then we'll come back and pick up 18. So this one's right out of your notes. We've been doing all this. So I don't know if I need to do this really with you. You know, I'll do it in case it's not in your notes. So that's S. I'm just going to do black, red, and black. All right. So S naught, J. I do this by column. A naught, V naught. That's the first time I've ever given it this way. I didn't do it this way last year or the year before or ever. And then the next row is the next one up, which and then here's somebody notice this. Oh, look, you can just do the diagonal. Oh, not quite, almost. It is true. That is the symbol. S naught, but you're gonna have to put a coefficient in front of it. We'll get that. And then J naught. Let's do it the easy way. Kind of like the magic, you know, it's like the beautiful pattern just for equations. A naught. And then we got V naught. And then we put in the coefficients. That's all one. This column is all 1. And then we get to the next one up, which is 1/2. So 1/2. And the next one up is 1/6. And the next one up is 1/24. You know, teaching chemistry for 12 years is probably why I keep making the connection to the periodic table, because the periodic table's got so many patterns on it, as far as how everything works, you know, gas, solid, liquid, how it all works together. You can glean from where it is in the periodic table as to what it's going to react with and all that. So I like to kind of make tables of motion, things like that, and tables of energy. But anyway, the motion's cool because it's something it's an observable, you see it. That's one reason why I spend so much time on motion. I spend more time on motion than anybody else, certainly in Oklahoma. I get criticized for that, but then again, proof's in the pudding. You guys end up doing, as far as classes, better than most anybody else does in Oklahoma. At OU, I don't know about OSU. How would I show jerk in terms of these other variables? So what I'm saying here, like if it's, how would I show jerk in terms of these other variables? Oh, okay. So if I'm looking at position, how would I show jerk in terms of position? So let's go with Newton's symbol first. Now Newton, and this is the first time I've asked this question as well, but Newton was into brevity, right? And so he would just call a jerk an X triple dot. If you remember that, you know, hey, you're a jerk, you're an X triple dot. A nerdy way to tell somebody they're a jerk in the hallway and they wouldn't know it. Then you and all your nerd friends laugh. And then he studies physics, and a couple of years comes to beat you up. Hey man, you calling me a jerk? Leibniz symbols. So Leibniz would have to say this. Yes, it's more complicated, but it's more thorough, which we're going to have to do. We have no choice. Once April, March gets here, we're going to have to start doing it the Leibniz way. But for now, we'll be lazy. So that's d cubed x over dt cubed is Leibniz way of saying it. Velocity, and I'm showing jerk. Well, for velocity, it's just v double dot, okay? And then we get the idea, okay, so for acceleration, it's a dot. See, that's why Newton's brevity, boom, 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 let's go. I said what I want to say. I did it the quickest way possible. I mean, you know, Newton's a genius. Leibniz methods seem cumbersome to him. Okay, as it might you, but I didn't like it either at first, and I grew to realize it was the right way, grudgingly. So d squared v over dt squared, and this would just be dA over dt. So you're just doing, you're just taking the thing and multiplying by ddt. ddt is like saying dot, pretty much saying I'm going to dot you. Yeah. Okay. Now the two hardest ones, and we got 20 minutes. All right. All right. I plotted it for you. Let's answer the questions first, then we'll tackle the graph. That's what I strongly suggest. So, man, this light is killing me. That's probably not good. All right, I'm trying to make it because it's really dark in here. So, all right. All right, what is the initial position of the object? Well, we just got finished doing this stuff. It's right up there. It tells you negative 75. Oh, can you see that? I guess you can see that. Negative 75. Okay. So that's easy point. And the one on the test, this, I want to put this and the last 21 on there. I don't know if I can get them both, but they're both pretty daggone important. What is the initial position of this object? So just negative 75. I mean, I'm not going to lie to you. This test is not going to be a walk in the park. You're in second semester physics now. What is the equation? But you know, we all the safety nets are there. We still the blue and black may come in more handy now. What is the equation for the velocity of the object? Okay, let's just do the derivative. So v of t 12t squared minus 96 t. You know, you could do, I think doing power rules like ASMR, I mean, it's very, you could, that could be your bit. You could be like the power rule ASMR, and you're just doing power rule all night and very gentle. You get close up to the microphone. All right, plus, then take little feathers. 180. Okay, so that's now my V naught meters per second. It says to graph it, but let's wait. Because you know, when you're graphing these things, as I had Mr. Patrick told you guys yesterday, always start at the bottom, work your way up, because you don't want to start with to try and graph the most complicated graph. I graphed it for you, but you don't want to start there. You want to start at the easiest graph and work your way up, because the lower graph tells you stuff about the upper graph, except it doesn't tell you initial conditions. That's why we have initial conditions. All right, show your work and determine the 2 times the object changes direction. So in this case, you can tell, if you just look at it, you can say, well, the object was starting off going, let's say north. This just north-south, by the way, this is one-dimensional motion. So it started off going north, but slowing down, then turned around at around 3 seconds, just a little bit. So we should expect a pretty decent sized initial velocity, but then a really small, velocity, and then a really small velocity on the other side of that, and then back to a positive velocity. So we know that if this is, we're assuming that is because it ultimately is positive. So we're assuming the velocity is a smiley face, right? It's a parabola, but it's a smiley face, not frowny. Okay. Show your work and determine the 2 times so it changes motion. So I'm not going to plot it, not right now. No. I need to know exact numbers anyway. I'll go ahead and just do it. Oh, really? It's quadratic formula. Of course it's quadratic formula, because it changes direction 2 times. So I got to use the quad. It's not the orange quad or the blue quad. It's the actual quad. Okay. Oh, all right. So, yeah. So T then, do I remember the original quad? T equals the opposite of B plus or minus square root of B squared minus 4AC all over 2A. And so in this case, yeah, because you're setting equal to 0. So your B though is 96 or negative 96. So that's going to be positive 96. I'm not going to do this work. I'm just going to let you do it, but I'm showing you. And then you take the B squared. So that's 96 squared. Here I said I'm not going to do it. 96 squared minus 4AC. Ugh. It's a big number. My calculator. All right, so 4 times 12 times 180. I got my phone here. Far be it for me to think. 4 times 12 times 180. 8640. Really? That thing is huge. Hey guys, tell me if I'm making math mistakes. 8640. I'm in my own little world here. 8640. Turn your mic on. Say something. I don't even look at the screen. Oh, but that's 96 squared. Okay, I was starting to worry there. Okay,
What are we doing this for?
What's this? I'm trying to find the 2 times. I'm trying to find, okay, this is asking me, when does it turn around? It turns around when the velocity is 0. when the velocity crosses, like remember on the velocity graph, this is backwards and this is forwards, right? So whenever the velocity crosses here, it's going from backwards to forwards. When it crosses here, it's going from forwards to backwards. You see what I'm saying? So if I can find out where the velocity is 0, I know where it turns around. So I could do it from the graph. I thought about doing that, but then I said, it's not going to be as accurate. But I didn't realize this quadratic formula would be such a mess. I'm not going to do it. I'm quitting here in a second and letting you guys finish it. But
can't you? Why do you need it? Why can't you graph it from the equation?
Oh, you're saying go on Desmos or something. Type it into Google. Yeah, I mean, as far as the thing is, though, you're on a test here. You don't have access to Google. You don't have access to it. Now, if you have a graphing, okay, that's what I was thinking about this today. I don't think it's fair. Some kids have had are pretty good at graphing calculators. And if you happen to have a graphing calculator, then that gives you an advantage on this one little part over somebody who doesn't. You know what I'm saying? So what I'm going to do is I think this is, except I'm running into a snag here, but normally it's faster solved without a calculator. And okay, so let's keep going. We'll come back to that maybe. We can always get it off the graph, and I'll let you be a little bit off on the graph. So let's go on to D. At what time will the object reach its highest speed? Now it reaches, that's called a point of inflection, right? The POI. We talked about that today in class, at least in second and third hour. We talked about it yesterday in sixth hour. But point of inflection is where the velocity is going the fastest, where the speed is the fastest, whether it's positive or negative, whether it's a positive slope or a negative slope. So this point of highest speed, A equals 0 there. So you find out where is my acceleration 0? And that's where the velocity is at its peak, either positive or at its trough in the fourth quadrant, where it's going the fastest it's going to go. And it only happens once on a cubic function. So I go ahead and take the derivative again. I get A sub t equals 24t minus 96. Okay, so, and that's meters per second squared. So now I can plot that sucker. So I come over here and I go, and it looks like it's going to be kind of a sketch because that's fine. It's negative 96 is where you start. Your slope is 24. So, okay, we'll go off these numbers. So 24, and if I get to 6, okay, so 6 times 24, that's 144, and I was at negative 96, so minus 96. So that puts me at 48. So at 6 seconds, I'm at 48. So come over here, and 48, I'm going to guess on that. Let's say it's right here. It's kind of important where I guess. So it'd be nice maybe to have a little more of a grid system. I'll put a better grid system on the test. And then you connect those up. So this is how acceleration is changing. And so you see it's a bow tie, but it's a lopsided bow tie. So there's my positive part. Here's my negative part. And then that means that this guy, this velocity, we go to the V naught, and V naught is, what does it say? V naught is, oh, we didn't do, V naught's 180. So that's right there, 180. I didn't ask you, but there it is, 180. So over here, you start at 180 for the velocity, 180. And you can see that right here is where you will not be at 0, but you'll be at your lowest point. So what you could do, and this is parabolic, what you could do if you're just going to plot it up, you can just look off the graph above. Good grief, look at that. So that's point of inflection. See that point of, if I keep going up, see that point of inflection? Let me make this nicer. Okay, check it out. If I go up to this graph above. You guys can see that, yeah. Okay, right there. And I kind of guessing a little bit, but that is the fastest. That is the point of inflection. The point of inflection occurs between the relative maximum, relative minimum on that X versus T graph. So right here is probably about where it would be. The point of inflection is actually right there. I'm off by a little bit, but that's not bad. So that's my POI. But
So
where this is, go ahead.
Why were you using the quad? Why are you solving for T? How is that going to help you graph it?
Okay. Now I'm getting to that right now, Cole. So here we go. So what I'm saying is, because I had that top graph, that's dumb to do all that work, because I can just go to the top graph and go, where is that velocity 0? Where is that slope 0? And the slope, it looks like it's 0 right here, right? If I ... and it's flat or 0 right there where it's a relative minimum. So that's 0. So I know that that's 0, that's the 0, and that is the most negative it's going to get, because see, it's a negative slope, and that's the point of inflection. And so it starts off positive. See the slopes, this, okay, let's blow this up. If I look at the tangent line to this, which is the derivative, if I look at the tangent line, come on, man. Here we go. If I look at the tangent line, in other words, kiss that curve, that's telling me what my velocity is. So I kiss the curve, and see, as I'm going up this curve and I'm kissing it, it's getting less and less steep. It's starting to flatten out. You see that? See that red line is getting steep, getting shallower and shallower. Eventually it flattens out right there. I was off a little bit, but right in there. Okay, it flattens out right there. So my velocity starts off positive, but goes lower and lower. In fact, finally flattens out right there, and then it comes down. I know it's a parabolic, and so it's symmetrical the other side. And there you go. And then it starts to head back up. So that's what V versus T looks like. Let me erase that forward back. Okay. And is this asking a lot for a high school student? Yeah. I'm not gonna lie. Some of the hardest stuff we do second semester right here. Go ahead.
How is the quadratic formula going to get us the 2 times that when the object changes direction?
No, the object. Okay, so notice that there are okay, hold on. There are, get out of there. 2 points, 2 times in which that velocity goes to 0. If I would have solved that, I would have got those two purple. I'll make them black. Those 2 times. That would have given me those exact 2 times. But
because of the plus and minus.
Yes, because one of them would have been plus, and the other one would have been the smaller one. They both end up being positive. When we're doing orange, we always got the orange quad. One was always negative, and that was the end. We didn't use it. But when you do blue quad, when something comes up and you're saying at what time is it at this velocity, you always get 2, not always, but if it's we'll get into this with projectile motion, but if it's a type, well, can't say type, if it goes up and comes back down, and they're both above you at 2 points, then you're going to get 2 positive times with blue quad. But you would really not get that with orange quad. You'd have to contrive a scenario. Finally, it says, what's the equation for acceleration? We did that. And then I did the POI. Just set that equal to 0. That'll give you the POI, point of inflection, the highest speed, whatever that is. What's it, 4? Yeah, 4. So at 4 seconds, should be POI. So that should have been 4. See, I'm off a little bit. It should be 4. But all right, okay. And then finally, a jerk is just equal to 24 J naught, 24 meters per second cubed. Oh, I got 5 minutes. Okay, and that goes over here and just go 24. Okay. Now let's look at the 21. And this is like the back of 4.7. And I have a help video on this. Yes, I do have a help video. I think we're going to go through all this whole thing. So let's do the easy part first. 4.5. Oh, okay. Hold it. I came prepared this time. All right, so I have these already done, and I'll unveil them. This will make it faster because I only got a few minutes. So I'll unveil them as you do them. So I'm assuming, walking around the room, I'll give you guys about 30 seconds, but I assume you already did the power rule 3 times. I'm gonna finish my banana. I've been trying to eat this banana now for about 3 hours tonight. I keep doing other stuff. Best fruit possible. A lot of sugar. Okay, now I'll unveil them. Pause if you're still working, if you're watching the recording. All right, that's what I got. Let's blow that up. Let's make sure we're all okay there. So really, this is easier. This is more straightforward, 21 is, than 18 was. But 18 was more real life. This is more mathy, okay? So obviously we don't want to do X first. I mean, let's try to do it without resorting to the graphing calculator or using Google. So let's go. Let's do the ones we know we can do pretty easily. Well, J jerk is 9. I can plot that. So it looks like this. Okay, just 9. So I'll blow it up. So there's your jerk, just equal to 9. And then the next one up would be velocity. Is that my velocity? No. Okay, so velocity is, well, don't look. I saw you peeking. Okay, so the velocity is not hard either, because you look at the velocity, hit pause if you're watching the recording. But I'm I'm sorry, no, not velocity, acceleration. The next one up. I'm thinking trio, it's quartet. So the acceleration is just 9t minus 4. So I can all plot that. And let's reveal. Okay, I'm going to take it off now. That's what that looks like. Let's blow this up. So remember, as I've been drumming into your head since September, the blue function is the slope of the graph above. That's why we've been doing it this way so long, ever since the duet in finger dancing. We've been talking about that. You know, the graph below is the slope, the graph above is the area. All right, with initial conditions. And so we use the initial condition here. We know that A naught is -4, and then it has a slope of 9. Okay, so I can plot that. And wherever that hits, wherever the acceleration hits 0, that's the point of inflection. That's going to be the fastest speed in the problem. Okay, so it looks like it has 1 point of inflection, which all cubic functions have 1 point of inflection. Okay, they have to, derivatives. So now I've got to plot that parabola. Well, this is a parabola, but it's the derivative of the parabola. So it tells you everything you need to know except initial conditions. Okay, let's find our initial condition. It looks like it's -6 for velocity. Okay, so I know the velocity starts at -6. I know that the slope of that velocity will be 0. Yes, the slope of the velocity will be 0 at, it looks like, a half a second. I know that it starts, I know that the slope it starts off with is -4, because that's initial conditions for acceleration. So it starts with the slope of -4, goes to 0, turns around right there at a half, and then gets steeper and steeper. So that's what you should sketch. Well, if I sketch that, I'm going to get this. Okay, now notice it started at, did I mess up? Oh no, it started at -6, okay, because that was V naught. But the slope right there, it starts at -6. Let me get rid of that. Okay, it starts at -6 right here. Yellow maybe. Okay, starts right there, but its slope right there, that slope is -4, because that was the initial See -4, that's the initial acceleration, which is the initial slope of the V versus T. And there's this, you see it right there, -4. So I know kind of how to draw it. Now, as to where this crosses, that's where you'd probably want to set that V equal to 0, which once again is that nasty old, and there's no graph above to guide you here. So that's the nasty old quadratic formula again. That's the original quadratic formula is on your equation sheet in case you know, B squared minus 4AC, you forget, whatever. It's on your equation sheet. Okay, so that would give you those 2 points, and then you would have everything you need. You got where you start, you got your turn around, you got those 2 points, you draw a parabola. Now the next one's a little harder. Now you're trying to plot this, and on a test like I did on the take home or the practice problems, I would give you that graph because it's not fair for those without a graphing calculator, but there is some stuff we can glean. So that graph would be given, but there is some stuff that we can get from this graph here of the parabola. I know where this is. I know where this is the steepest. It's right there at the point of inflection. So I know that is negative steep. So if I just try and draw on this, I know right up in there, I got a negative. It's a real negative steep because that lines up with my point of inflection. I know that the slope is flat here, and I see that, and it's flat here. So it must be the low point somewhere in there. So even without, and then I could run some numbers, but even without doing much to it, I can see that, okay, I wasn't far off. I could see that one. And I got that slope about right, and that's flat. So I could have connected those up and got a pretty much and I would have accepted that. But I'll give you the cubic part, okay, like it was on the practice. Okay, I'm worn out, man. It's 10:03. I ate my banana. I got nothing else. Questions? Oh, Carson said, will graphing calculators be legal still? Yeah, I mean, I'm just happy you guys have a calculator at all. You can't use your phone, can't use your laptop. I'll give you the only one they might struggle with is this one a little bit, but if they have that one, they can go off the slope and get that one. And I'm going to be a little lenient on, you know, if you're not exactly right. I haven't written that question yet, so I'll write it tomorrow during butt ball. And then Patrick said, will the Leibniz method be on the test? You mean the D squared? It could, well, it was on the practice problem, so it certainly could be, you know, D squared X DT squared for, yeah, I'll probably put something on there on that. It's easy to stick it in there. So you do need to know that it's not, you don't get that reference sheet. I'm still working on that reference sheet, but I'm not going to give everything to you and give you a test. So you will get on 1 or 2 more reference sheets, but you hardly ever get a reference sheet on current material. That's what you're supposed to know. You know what I'm saying? Not just read off a reference page. All right, what else we got? I was recording, yes. Please tell me. Yeah. Okay, I'm recording. So I will put this on the group. I'll put it on the YouTube channel. I'll put a link on the group, and you guys can watch it. You know, hey man, maybe it goes viral. What do you think? Yeah. Oh, I know what'll go viral is that ASMR, that power rule ASMR. You know, that's very soothing. So very soothing. So I'll get my feathers out, and next time we'll do an ASMR. Okay. I have feathers and I have little bells I ring and stuff. We'll do this little clip stuff. Okay.
Just started off with a rain stick.
Oh, yes. I like that idea. And then I'll be the physics guru. We'll talk about seal deep and burn incense. Okay. That's not a bad gig, man. I'm thinking of something for retirement. All right, so I'll see you guys. Have a good evening. Unless you, adios. If you have a question, a particular question, you stick around. And Grace, Leah, Michael, and Samara are all four asleep. Oh, Michael said, okay, Michael, Grace took off. Michael took off. Leah, Samara, you got a question? Are you away from the computer?
Actually, Mr. Oski, I do have a question.
Yes.
Okay.
Samara is ironing her hair right now. My sister, she had straight hair today. My sisters used to iron their hair. Go ahead, Leah.
On 21, on the
Yeah.
graph that we're showing right now, how did you get the point of inflection?
That is found from the acceleration graph. Wherever that situation, I won't give you a snap. I mean, in a jerk situation, a quartet, the acceleration will always be linear. And if it never crosses the 0 point, then there's not going to be a point of inflection. I should have brought that up. If it never goes from the first to the fourth or the fourth to the first quadrant, then there won't be a point of inflection. So acceleration, so to answer your question, point of inflection is when the acceleration is 0. It's counterintuitive. What I'm saying is the fastest the object is moving is when it's exhausted its acceleration. So I guess it's not that counterintuitive, saying it that way.
Okay.
And then one other thing, Leah, then you're still there. So you can follow that on up. If this were lined up, you could follow that on up, and just put a ruler on it. And then that's the point of inflection on all the graphs above.
Okay.
Yeah. And you can't see it on the jerk because it's just constant. Jerk doesn't help a lot. Sets the stage, but it doesn't give you initial conditions or other things. Okay.
Mm-hmm.
All right.
And one more.
Yeah.
On 18, on the velocity graph.
Yeah.
How did you get that lower point? I got the other two, but I didn't get that lower one. Like the negative.
This point right here, that was what I was just saying about. That's the point of inflection. I'm sorry. No. It's a point of inflection. It's a point of inflection on the X versus T, but it's the relative minimum or maximum on the V versus T. Just like, look, like this lines up right here. That occurs right there at a half a second. It also occurs there at a half a second. So, but notice it's the same here as it is on 18. That point of inflection, when the acceleration is going from negative to positive, that's where you have the low point, it's a low point on the bowl, but that means this is all, it's all formal, kind of mind blowing, but that means that's where this object here is going backwards the fastest because that's negative. But whatever this little particle is, an electron or something coming along, it all of a sudden hits a magnetic field and just whoop, immediately turns around and then hauls butt backwards for a few seconds and then turns back around because now your velocity goes from negative to positive. But that's what a jerk will cause something to do.
Okay. Turn
around twice.
But is that lower point on V a specific number?
Yes. To find it, if you wanted to actually find out, what I did was I realized it was 0, 0 there at the 2 and at this one. And I realized it started at -6 and it had a slope of -4. And then I just looked up here. Well, I looked here, I knew that the lowest point was at 1/2. And so as far as how low to make it, I mean, if that's -6, you might ask, well, why didn't you go on -8? Why did you pick that point as how low you went? You could plug in half a second for the velocity and then see what you get. Or you can just kind of follow a trend. That looks like that slope's coming down. It's come back up over here. And I'm cool with just kind of doing this. I mean, you know, I'm conceptually grading this. So did you get the concept? I mean, you're off by a half a, that's, if it was worth 50, you'd lose a point. You know, if you, as long as you get the shape. What?
Is that idea the same for 18? Like that lower point is just
Same idea, same idea. So on 18, same idea. So I wasn't quite lined up right, but it should be at 4 seconds because that's what this is telling me. So that's point of inflection. So that means that this thing really should have come over, and I would have accepted what I have here. I would have given credit on that. That it should come over a little more, maybe then come back up, but that's fine. And then it's just, you can also use law of symmetry. I mean, you know, this side has to be symmetrical to this side. Looks like you don't go as far on this side, but this is all beautiful symmetry on the V on parabolas. That makes parabolas faster. If you can get half it done, you got the other half.
Okay, that makes sense.
Okay. All right.
Thank you.
See you tomorrow. Bye-bye.
Bye-bye.
Okay, I'm going to end this thing, I guess. Go up here and stop sharing. Stop sharing. Okay. Now, I'm going to end it. And end meeting.